we have studied about the addition reactions of alkynes with hydrogen, halogens and hydrogen halides. Now we have started discussing about the addition of water with alkynes. There we have seen that alkynes do not react to water in general conditions. They react to water in the presence of mercuric sulfate and sulfuric acid at 333 Kelvin to form carbonyl compounds, that is aldehydes and ketones. Okay. So, let us take ethyne. Okay. Ethyne. So, we add water in presence of Hg2 plus and H plus at this temperature. Okay. So, one carbon will get the hydrogen and another carbon will get the OH group. So, one carbon gets the hydrogen and one carbon gets OH group. Now, this type of structures, when the double bond and alcohol group are on the same carbon, we call it enol. Okay? That is in and all. Now, these type of structures can undergo isomerization to form carbonyl compounds. Like this. Okay. Now, these two are isomers. Why? The molecular formula of this compound is C2H4O, right? Here also the molecular formula is C2H4O. This type of isomerization is called ketoenol tautomerism. Although in this case this is not a ketone, this is an aldehyde because this carbon was not bonded to a second carbon atom, but this type of isomerization is called generally as ketoenol tautomerism. Okay. So, ultimately it forms ethanol. Okay. Now, if we take propyne, we take propyne. Okay. So, when we add water to propyne, the reaction conditions are same. So, now Markovnikov rule will be followed. So, hydrogen will be added to the carbon having more number of hydrogen. So, this carbon has one hydrogen, this carbon has no hydrogen. So, hydrogen will be added to this carbon. So, we get this and OH will be added to this carbon. Again we can see that a enol structure has been formed. So, now again it will undergo isomerization, that is ketoenol tautomerism, and in this case it forms ketone. Why? Because this carbon is also bonded to two carbons on both sides. So, this forms a ketone which is called propanone, or the common commercial name is acetone. Acetone is a very common organic solvent. Okay. So this was another example of ketoenol tautomerism. So with this, we have completed the addition reaction of alkynes. Now another type of reaction of alkynes, which is polymerization. So like alkenes, alkynes can also form polymers. So there are two types of polymerization of alkynes. One is linear and the another one is cyclic. Okay. So for linear polymerization, we have ethyne. So ethyne can polymerize under suitable reaction conditions to form this. This is called polyethylene or polyacetylene, because a commercial name of ethyne is acetylene. Okay. So polyethylene or polyacetylene. Now this polyacetylene, it is a very good conductor of electricity. Okay. And it is also lighter and cheaper than metal conductors. Okay. So thin films of polyacetylene is used for electrodes in batteries. So these are the applications of polyacetylene. This was linear polymerization. The second one is cyclic polymerization. Okay. This one was linear. Now the second one is cyclic. Cyclic polymerization of ethyne gives rise to a very interesting class of compounds that we will study as our next topic. So, three molecules of ethyne polymerize to form benzene. Okay. When passed through red hot iron tube at 873 Kelvin, that is around 600 degrees Celsius. Okay. So at extremely high temperature, when ethyne is passed through red hot iron tube, they polymerize to form benzene. So let's write the ethyne molecules in this way. Okay. Red hot iron tube at 873 Kelvin. So, the bond formation is something like this. Okay. So, these pi bonds break from each molecule of ethyne and the bond formed is like this. So, 2 pi bonds are left. Like this. This is called benzene. Now, benzene has two resonance structures, that is, these double bonds can rotate. So, another structure will be like this. Okay. So, overall is benzene written like this, a cyclohexane ring with a circle in between, that is, the rotation of these double bonds is described as a circle. Okay. So, these are called aromatic hydrocarbons. Okay. Benzene is an example and benzene is the most simple aromatic hydrocarbon. Okay. So, before moving on to the discussion of aromatic hydrocarbons, let us conclude the study of alkane, alkene and alkynes with an interesting conversion. So, this is the question that how will you convert ethanoic acid to benzene. Okay. So, how will we convert ethanoic acid to benzene? So, ethanoic acid is this. Okay. And benzene is this. As we have studied that benzene is formed from the polymerization of alkynes, that is ethynes. So, first we will have to reach from ethanoic acid to ethyne. Okay. So, we have to convert ethanoic acid to ethyne somehow. That will occur when we can convert ethanoic acid to alkane first. So, what do we know? That for the conversion of acid to alkane, we have decarboxylation, right? So, decarboxylation occurs with sodium salt of the carboxylic acid. So, we have ethanoic acid or acetic acid. We treat it with sodium hydroxide, aqueous sodium hydroxide. So, it will form sodium ethanoate. From sodium ethanoate, if we react with soda lime, that is sodium hydroxide and calcium oxide accompanied by heat, we get methane, that is CH4. Okay. Now, by controlled halogenation, we had studied the halogenation of methane. So, halogenation of methane forms multiple products, but each of those products can be isolated by controlling this reaction. So, from controlled halogenation of methane, we can get this. This is methyl chloride. Okay. Now, we had read Wood's reaction where from two molecules of methyl chloride reacting with two equivalents of sodium, we get a carbon-carbon bond formation. So, here we add sodium in dry ether. This is the Ur's reaction. Okay. So, what was Ur's reaction? It was like this. So, 2 NaCl was liberated and we got CH3, CH3, right. So, from methyl chloride, when we reacted with sodium in dry ether, we get ethane. Okay. So, from methyl chloride to ethane. Now, we have got alkane. The required alkane has been achieved. Now, we will convert it to alkene, then to alkyne. So, now if we add chlorine to ethane, so chlorination of ethane will be similar to the chlorination of methane since both are alkanes. So, chlorination of ethane will give this CH3 CH2 Cl, that is ethyl chloride. Now, ethyl chloride can be written like this. If we want to convert it to ethene, we will have to react with alcoholic potassium hydroxide, right. So, potassium hydroxide will take this hydrogen, the bond will break, and with the liberation of potassium chloride and water, we will get ethene. Okay. Now, we have to convert ethene to ethyne, right. Now, if we react ethene with Br2 or Cl2 for that case, so we get this 1,2-dibromoethane, right. Now, how we will convert it to ethyne? At first, we will again treat with alcoholic potassium hydroxide. We will get this. Then we will react it with sodamide and we get ethyne. Now, we have received ethyne. Now, we can convert it to benzene very easily by red hot iron tube in 873 Kelvin, we get benzene. Okay. So, with this we have completed the discussion of alkanes, alkenes and alkynes. In the next lecture, we will start aromatic hydrocarbons. Thank you.